Okay, so what I'd like to do in the second part of the lecture is cover a first example of a differentially private algorithm for this loss minimization problem, the CRM problem. And our first example, our first kind of approach will be to run, to try using the exponential mechanism. So let's assume, so what we're going to do is we're going to assume that our loss function is delta bounded, so it maps a parameter vector and a data point into some range, 0, delta. And then that will allow us to run the exponential mechanism. So remember, we're defining the loss as the sum from I equals 1 to n of little loss function applied to each of the data points. And what we'll do is we'll construct a distribution. We'll sample W hat from the distribution that is proportional to something that is exponential. So it's proportional to e to the minus epsilon n over 2 delta times the loss at W. Okay, so this is our algorithm. So maybe, it's actually like not even crazy to work out like a very straightforward example of that. So for example, if I've got the mean, if my, depending on where my data points are, the mean, the loss function is quadratic. And it has a unique minimum at the actual mean of the data, the sample mean of the data set. And so that's what the loss function L will look like. And so what the corresponding exponential mechanism will do is it will actually sample from Gaussian. And so that is only, we know it's only valid, that's only going to work if you're working on some like bounded set, right? And indeed for, so this only, the loss function is delta bounded. So L is delta bounded only if we constrain the data and the parameter. So let's say if X and C are both equal to the set, like 0 to square root of delta or something like that. And what this says is if you sample, like, restrict your sampling to that set. So, oh yeah, I guess I should have explained that we're sampling a vector W within the set C. So our distribution is only over the set C. So for example, if you try to use it for the mean, you'll get some like truncated Gaussian distribution, which is actually like not a great way to compute the mean differentially privately. We kind of know that at this point. That there are better ways to do it. But it's still this is a kind of a totally generic approach, and we'll see that it actually gives us something pretty interesting in sort of full generality. And especially when if you write down what it gives you for like more complicated like linear models like logistic regression or support vector machines, it's already a much more interesting kind of approach to take. Okay, so the first thing to notice is that this is always differentially private. So it's epsilon 0 differentially private if this algorithm is epsilon 0 differentially private if L is really delta bounded. And that's because L is going to be, the sensitivity of L is going to be at most delta over N. Okay, and so delta over N, notice, shows up here as sensitivity. Right. So a more interesting question is, well, when is this thing useful? And you can prove a number of things about it. It's actually a style of algorithm that gets used a fair amount in the learning literature for reasons that have nothing to do with privacy. But we'll try to write down just something as sort of relatively straightforward as we can. So here's a result. So suppose that C, our constraint set, is just the L2 ball of radius of some radius R. So let's say C, which lives in R to the D, is the L2 ball of radius R. So that just means it consists of all vectors that have norm. Sorry, that's big R. And suppose that L is G Lipschitz continuous. And we run the exponential mechanism with boundedness delta equals G times R. And it turns out that's okay. So it's you can argue that any G Lipschitz function on a ball of radius R is in fact delta bounded in the way we need for the privacy proof. So I'll leave it as like an exercise to think about why that's okay. Is this differentially private? So believe me, it is. Then what we get is the output of the algorithm satisfies like a reasonably okay guarantee. So this is for all x, the worst case over the data. I can look at the expectation of the excess loss, the risk here. So that's the expectation of this loss minus the minimum over C of loss WC, WX. So that expected excess risk is going to be bounded by something that depends on G and R. Okay, so for the purposes of the proof, maybe it's easier to just think of them as 1 times D over epsilon n and an additional log factor of epsilon n over D. Okay, so this is the statement that we can use. We can sort of take to the bank, which is that when you run this on a if the loss function is Lipschitz, then and you're running it on a constrained set, so in this case a ball of radius r, then your loss function will go to 0 roughly as long as the number of data points you have is bigger than your dimension, right? So this is small when n is much bigger than d, and well, really d over epsilon. Okay. So that's actually pretty good. It means it gives me kind of a measure of complexity of the problem. In this case, it's the dimension, such that once I have enough samples, I can really get my hands on a good solution. And like once the number of samples I have exceeds that sort of underlying complexity of the problem. Now, we'll actually see that there's nothing kind of holy about this dependency on D. It turns out we can get for one thing, we'll see an algorithm that whose dependency scales more like square root of D under approximate differential privacy. And then there are other things we're not going to cover, but that other algorithms that kind of allow us to exploit other structure, not just the dimension, but other structure about, say, the constraint set and various other things going on that allow us to get more kind of refined bounds on the accuracy. But at least for now, this is our first pass, and this is going to give us something, I think pretty interesting to start off with. So before we jump into the proof of this, maybe it's interesting to ask if this algorithm can be made efficient. So this is this pretty weird algorithm where we define this like function, this probability distribution that involves, we're now taking samples of this continuous set. So it's like a continuous probability distribution with this like weird e to the whatever function. Turns out, nevertheless, the answer is yes. Well, sort of. If L is convex. But no, not in general. And even when it's convex, this is sort of polynomial time, but not super efficient. The algorithms for sampling from these general, what are called log concave distributions, because you've got a convex function that's been put in the exponent with a minus sign in front of it. So there's general algorithms for sampling from that type of distribution, but they're not currently super practical. And so for example, for things like deep neural networks, this approach is really not going to be practical at all, and we're going to have to take a very different approach that we'll talk about next time. All right. So let's see why this is. All right, so let's fix our data set. And we'll rescale everything so that G and R are 1. So it turns out you can sort of rescale the ball. You can just rescale everything so that you're operating on a smaller ball, and also change your function values so that the gradients are smaller. You could rescale the function, and it turns out that will get the right behavior, or that will that kind of rescaling will just when you undo the rescaling, you'll just reintroduce GNR in the right place in the bound. Okay, so I'm not going to work through that, but without loss of generality, we can take GNR to be 1 in the proof, and it's easier. Just have fewer symbols floating around. All right, so we're going to fix a data set X, and we're going to look at this loss function L, L of W, which is really L of WX. So we've got this this ball C and a loss function that's defined on it. And so that C has some true minimizer. Let's call it W star. Okay, so let's say let's let W star be the actual minimizer of the function. And what we want to argue is that this exponential mechanism is going to produce something kind of in the neighborhood of W star, like something with a good function value. It doesn't have to be close to W star, but it has to be in the part of the function. So there's sort of like the part of the function that where the function value is low, and whatever points in C that corresponds to, that's where we want our output to come from. So we're going to take a small radius r. We'll pick a small number r. And how small? Well, we'll see later, but it's going to be something like 2d over n epsilon. But we'll see where that comes in down the road. And we'll define two sets. So we're going to look at our good set. So these are the W's where the loss is at most whatever the optimal value is plus little r. And the bad set, these are the W's where the loss is at least sort of that thing plus t. Okay, so in the past, when we analyzed the exponential mechanism before, we said, okay, there's at least like one good output, and that one good output will have enough probability mass that I'm going to produce it with reasonable probability. In this continuous setting, that's not true anymore. There's no like single output that has any probability mass at all. So instead, what I'm going to do is I'm going to identify a set of good outputs, and I'm going to argue that the good outputs have enough mass. So, really what I'm going to do is I'm going to show that the bad outputs don't have a lot of mass. Okay, so let's just try and understand these sets a bit better. So there's the bad set. Like really, that I don't know too much about this. This could be like pretty much everything. But the good set, like maybe I can say something about that it contains, what can I say? Well, it has, it contains W star for sure. That's good. Check. What else can I say about it? Well, I can say it contains all the points, points that are sufficiently close to W star because my loss function is Lipschitz. So if I've got some vector W that's in C and it is within distance little r of W star, it's within distance little r of W star, then the loss at W is at most loss of W star plus r times g, which I've taken to be 1 here, so that's r times g. Sorry, that's just r. Sorry, that is loss of W star plus r. And so what I know is that this W is in my good set. So this good set is not like nothing, right? So basically, what I don't know exactly what my set C looks. Well, I know the set C is a ball rather. But I don't know exactly where W star is in C. But in some sense, that like the worst case is when W star is like right on the boundary. And so, I can look at the things that radiate within distance r, little r of W star. And what I want to argue is that there's a lot of stuff in there, that there's like enough stuff in that ball of radius little r, the good set. So who knows what, sorry about that. Who knows what good itself looks like? Good itself is sort of like, some larger set. But what I want to argue is that this sort of ball around W star contains a fair amount of mass. And one way to see that is that I don't really understand how it intersects with the boundary of C, but I understand that like I can find a ball of radius half of r that's entirely contained in C. Okay, so the ball centered at W star, something a little bit closer than W star. So it's actually W star minus 1 times 1 minus r over 2. If I take the ball centered there of radius r over 2, it is entirely contained. It is contained in both the constraint set and good. I guess that's redundant. I mean, it's in good, which is by definition like in C. But, okay. So what does this mean? It means that if I go to, if I look at the volume of stuff in the good set, I don't know exactly how big that is, but it's at least, like I want to compare that to the volume of stuff in the bad set, because we'll see why that calculation is going to come up when we actually compute the probability, but just stay with me for now. We're looking at the ratio of the volume, the volume of good things to the volume of bad things. The volume of good things is at least the volume of a ball of radius r over 2. And the volume of the bad things is at most, well, everything. So it's at most the volume of a ball of radius r. Okay, and so the formula for the volume of a ball in d dimensions is a little complicated, but the cool thing about that formula is it scales very cleanly. So if you double the radius of a ball in dimension d, you multiply its volume by 2 to the d. And if you triple its radius, you multiply its volume by 3 to the d. If you quadruple its radius, you multiply its volume by 4 to the d, and so on and so forth. Just like in 3 dimensions, when you double the radius of an object, you multiply its volume by a factor of 8. So the ratio of, I don't need to know exactly what the formula is for the volume of the ball. The ratio of these two things is exactly r over 2r to the d, and we took big R to be 1, so that's really just r over 2 to the d. Okay, so that's nice, because that gives us like a good handle. So that like r to the d is very small. R is a small number here. So r to the d is very small, but it's not 0. It gives me a handle on stuff. So now if I want to know the probability of the bad set, the probability that W hat lands in the bad set, that's at most the probability of the bad set divided by the probability of the good set. Because the probability of the good set is less than 1. So if I divide by that, it's okay. All right, and now the stuff in the bad set, so that's everything in the bad set has score that is at most e to the minus, so I had this like, I had a capital delta, which I simplified away to be 1, so I don't have to worry about that one anymore. So I had like epsilon n over 2 times the loss of W star plus R plus T. And then the volume of the good set was e to the minus. So everything in the good set has score at least epsilon n minus minus epsilon n over 2 times the loss of W star at W star plus R. Okay, and now what we see is that there's a bunch of stuff that cancels. So this cancels with that. And then for this ratio, we know what we've got its value over here. So we can just sort of plug that in. And so what do we get? We get like 2 over R to the D. So it's at most 2 over R to the D times e to the minus epsilon n T over 2. Okay, and so now at this point, I claim we're pretty much done. The rest of the proof is just a little bit of arithmetic. Okay, so what I'm going to do is I'm going to set, so for any given if I want to like show that the probability of something bad happening is at most some small number beta, so I've got given some number beta bigger than 0, I'm going to set t as follows. Maybe to see why I'm going to set it this way, it helps to rewrite this a little bit. So I'm going to write this as so this is like d ln of 2 over R minus epsilon n over 2 times t. And so I want this whole thing to be something, the expression inside the exponential to be something like log 1 over beta. And so I will set t to be 2 over epsilon n times d log 2 over R plus log 1 over beta. To get, and then the, if you set t this way, the probability of the bad set is at most beta. And then once we do that, we can set R the way we talked about earlier, 2 over epsilon. And if what we know is that with probability at least 1 minus beta, we have excess risk, or like error, is at most, we said it's like R plus T, right? So R plus T here is 2D over N epsilon plus 2 over N epsilon times D times log of D over N epsilon plus log of 1 over beta. All right. So this gives us a high probability bound. And we've seen this trick before that, when we want to go to get an expectation bound from a high probability bound, the thing to do is to recall that for every non-negative random variable, for z non-negative, we have that the expectation of z is just the integral of the probability that z is greater than little z, d, z, z greater than or equal to 0. So that's just like a formula you can use. And it has the implication that is, if you sort of integrate over the set of things where beta is like, less than, well, 1 basically, or less than a half, then what you get is that the consequence is that the expectation of the excess risk, which is indeed non-negative, so that's like loss of w hat minus loss of w star, is a big O of d over n epsilon times log of d over n epsilon. And we're done. Okay, so around something weird happened in the recording. Hopefully it'll be okay. So we're done with this proof. So what have we shown? We've shown that if we do this exponential mechanism idea, we actually get like a reasonably good solution to this general like convex, sorry, not convex, but continuous exponential, this continuous optimization problem. And what we'll see is that we'll see in the next lecture, we'll see other approaches to this problem. Now, what I'd strongly encourage you to do is look over maybe if you, depending on whether or not you've seen the notion of convexity before, I'd encourage you to sort of brush up on it. And we're not going to need a whole lot of stuff about convex sets and functions, but you should be like reasonably comfortable with the definition. So I'm going to go over the definitions quickly today, just to get them like loaded in your head. And then we're going to use them in the next lecture, and we'll do some exercises with them in class first just to get them like kind of, into active memory. So a set C is convex if it has like no holes or like places where the angles are greater than 90 degrees. So it's convex if for all x and y in C, the line segment xy is in C. Okay, so this set is not convex because here x and y can't see each other within the set C. Okay. This set is convex. Yeah. So is this one. Let's see. This one is, if this is C and like this is outside of C, then this is like not convex because it's got a hole. And again, x, I can find 2 points where the line segment is not completely contained in C. This is assuming that C is like the donut. Okay, so that's what it means for a set to be convex. Incidentally, another like a kind of a nice way to think about convexity often is that if C is convex, and I've got some point Z that's like not in the set, then I can find a hyperplane that separates Z from C. So what a hyperplane is, like a set of the form, you know, like A plus, sorry, it's those, you know, those vectors X that satisfy X minus A times inner product with some fixed B equals 0. So it's like some high dimensional space of dimension like n minus 1, or d minus 1, I'm sorry. So if C is a convex set and Z is a number, then I've got a hyperplane. I can, if Z is something outside of the set, I can always find like a line that divides Z from the set. And notice that's like that's not true for non-convex sets. Like if I take this Z, there's no way to separate it from the set with a line of infinite length. All right, so functions are convex. So it has to, for a function to be convex, it should be defined on a convex set. And it takes real values. And a function is convex if, so here's its domain of definition, C. Function is convex if it looks like this, okay? Or like this, or like that. But not like this. That's not convex. So it has to kind of angle upwards. And so F is convex. The nominal definition is for all, standard definition is for all X and Y in the domain, we have the following functional inequality. So like specifically, you know, if I take, you know, X here and Y here, and I look at like these 2 points on the function, and I sort of look at the line segment connecting them, the midpoint lies above the graph of the function, or at least not below it. So like, for example, the reason this thing isn't convex is here the midpoint lies below the graph of the function. So that's a definition of convexity. It turns out like this definition of convexity, it's very simple and very clean. It's not actually that easy to work with. So an easier definition to work with that's equivalent is the following. So if C is convex, and F is a function from C to R, then, and this, again, this works in any dimension. F is convex if and only if the following holds. If only if I can find an affine function G that depend, sorry, for every X in the domain, I can find an affine function G that lower bound. So what's an affine function? It's like a linear function, but it can have an offset term. So so G can, that means G can be written, G of X at value Y can be written like, well, I'll write out the formula in a second. Okay, so such that G of X, G sub X at x is equal to f of x, and g sub x at y is less than or equal to f of y for all other y's, for all y in the domain. Okay, so what does this mean? So so what does it mean? First of all, what does it mean for a function to be affine? And in this case, it means that it can be written as like f of x plus a linear function. So there's some w such that I can write g sub x in this way. And so the picture you should have in mind is that at any point on the function, if the function is convex, at any point I can find a tangent curve, a tangent line, tangent function that's affine, so it's like a linear function plus an offset, and that touches the function at that value at x. So if I take some other x, x prime, I'll get like a different g sub x prime, g sub x prime. And the important thing is I can find this affine function, and it's always a lower bound. So I can always kind of get a lower bound on my convex function by gluing like a linear, not linear, but affine function like right up against it. And if you sort of think about examples of non-convex functions, you'll see that like doesn't work for non-convex functions. So this, when f is differentiable, this g is actually the Taylor approximation. So when f is differentiable, g of x at y is equal to f of x plus y minus x times the gradient of f of x. But this makes sense even when f is not differentiable. So for example, for the absolute value function, I can find, it's like not differentiable at the origin, but I can find like actually several affine functions that have the right property that they're like affine, and you can glue them right up against the function at that point, and they'll provide a lower bound. Okay, so if you've never seen convex sets and functions before, you might want to like, look at a couple of examples, but these are the basic properties we're going to need, and so this should be enough to work with for now in the class. Okay, I'll see you guys in class. Bye-bye.